Okay. So given a graph, an independent set is a set of vertices such that there is no edge between any two vertices in that set. So for this graph, V2, V4, V6 can form an independent set such that you take any two vertices in this set, there is no edge between them. Similarly, V4, V6, there is no edge between them. V2, V6, no edge between them. So obviously, an empty set can also be called an independent set because it still satisfies the definition. There's no edge between any two vertices in that empty set. So that means we really want to maximize the size of this independent set. So given a graph, what is what is called the maximal independent set? It means the largest possible grouping of vertices such that there's no edge between any two vertices in that set. That's what we target for an independent set, a maximum size independent set. Now, in the case of vertex cover, the definition is again a set of vertices such that for every edge, there at least one of the two end vertices is part of the vertex cover. So that's the definition of vertex cover. So take an edge V1, V2, at least one of the two end vertices is in the vertex cover. V2, V3, at least one of the two end vertices is in the vertex cover. V3, V6, at least one of the two is in the vertex cover. So that means if I consider all the vertices in the graph as my vertex cover, then it obviously satisfies the definition too, because for every edge at least one of the two end vertices is going to be the vertex cover. Oh, again note the definition that at least one of the two. So in the case of say V3, V5, both the end vertices are in the vertex cover. That is fine too. So that means what we want to minimize is minimize the size of the vertex cover. So as I said, the entire set of vertices could be also considered vertex cover. That's an obvious solution. So what we really want is a minimal vertex cover. So now if you look at it, the independent set and vertex cover are kind of complement to each other. Now why is that? So because again look at the definition of independent set. If you take some set of vertices as independent set, then there should not be an edge between any two vertices in that independent set. Now looking at that from an edge point of view, so if there's an edge between V1 and V2 in the graph, both V1 and V2 cannot be part of an independent set, because if they are part of the independent set, if both V1 and V2 are part of the independent set, it violates the definition of independent set because there's an edge between V1 and V2. So for an edge V1, V2, both cannot be part of an independent set. That means at least one of the two end vertices, V1 and V2, should not be part of the independent set. Okay. So if we build a set that is complement of an independent set, so what I mean by complement is the vertices that are not in the independent set but that are in the graph. So if I build such a complement set, then for every edge, at least one of the two end vertices should be in that complement set, because both the end vertices cannot be part of the independent set. At least one of the two end vertices should not be in the independent set, should be in its complement. And such as complement set of vertices of an independent set can be then considered as vertex cover. So if V2, V4, V6 is an independent set, then its complement, which is V1, V3, V5, can now be considered as a vertex cover. So it satisfies the definition that for any edge, at least one of the two end vertices is now in the complement set of the independent set, which is the vertex cover. So if you determine a maximum independent set, then the complement of a maximum independent set will automatically be a minimum size, because you're maximizing size of independent set and find the complement of such a larger set, which is going to be a smaller set. So that's the minimum set. So that's the minimum vertex cover. So if you are able to determine a maximal independent set, we automatically have a solution for a minimum vertex cover. So that's what we saw last time. We saw one algorithm that can be used, a heuristic actually, that can be used to find a maximal independent set, and using that we can find a minimum vertex cover. So why I say it's a heuristic, not an algorithm, because all these things are NP complete problems. So we don't have an algorithm that can give us the optimal solution or guaranteed to give the optimal solution in polynomial time for any graph. So that means it's non-deterministic in nature. For some graph it may give us a maximum size independent set. For some graph it may not give the maximum, it may give you only approximate to the maximum. So we saw that in the traveling salesman problem. Okay, so now what a clique is again a set of vertices such that now you have an edge between any two vertices in that set. So if I say v1, v2, v5 form a clique, then there should be an edge between v1, v2, between v1, v5, between v2, v5 and so on. So between any two vertices in the set there should be an edge between them. That's when we call it as a clique. So if there are three vertices in the clique, then they should really form a triangle because there should be an edge between any two vertices in the triangle. Now, if there are four vertices that are part of a clique, then there should be an edge between any two vertices. So it should be like, there should be an edge. Say if v1, v2, v4, v5 can form a clique, then this is not a clique because there's no edge between v2, v4. So if there's an edge between v2, v4, then we can say v1, v2, v4, v5 form a clique. So in that sense, even an edge, so every edge is a clique of two vertices because v1, v2 can form a clique of size 2 because there's an edge between v1, v2. So again, an obvious solution is every edge is a clique of size 2. So what we really want is not obvious, we want something that is kind of not obvious and we need to have something algorithm or heuristic to determine it. So that's why we aim for a maximum size clique in a given graph. Okay, so in this graph, of course, as I just said, there's no clique of size 4. So we really have only triangle here. Okay, so now there are several triangles here. So v1, v2, v5 is a triangle, v2, v3, v5 is a triangle. There are several triangles. So again, it determines on how your heuristic breaks the ties and goes ahead and determines the clique. Okay. So we saw one algorithm heuristic for this. So let us go ahead and see one example for this last time. So we'll do one more example and move on from there. So this is the given graph. Now the heuristic name is called the minimum neighbors heuristic. Now is a greedy strategy. The idea behind the heuristic is to first, so of course the heuristic can by itself used to find only an independent set. Which is a maximal independent set. Now, using that, we will be able to change solution or kind of transform the solution or transform the input graph itself and find the other two. So that's what we're going to see. So let us just run the heuristic now on the graph and first find the maximal independent set that is possible on this graph. Okay, so for that, we need to determine what is called the number of uncovered neighbors for each vertex. So to begin with, no vertex is covered by any vertex in the independent set. So we say just the number of neighbors is same as the number of uncovered neighbors. So for v1, we say v3 and v4 and v5, or it's two uncovered neighbors. So that's 2. For v4, v1, v2 are the two uncovered neighbors. For v2, v4, v5 and v3 are 3 uncovered neighbors. For v3, v2, v6 are 2 uncovered neighbors and so on. So simply the number of neighbors is the number of uncovered neighbors for a vertex to begin with. Now we prefer to include, so we go through iterations and each iteration will include one vertex to the independent set. So which vertex we should include in the independent set? That vertex that has the lowest number of uncovered neighbors. So why we prefer for the lowest instead of say the maximum is that if you go for the lowest or basically if you include any vertex in the independent set, then its neighbors are being ruled out from being part of the independent set because there cannot be an edge between any two vertices in the independent set. So if a vertex gets included in the independent set, its neighbors are automatically getting excluded from the independent set. So if I include a vertex with lot of neighbors, then all those neighbors are going to be excluded from the independent set. So the size of the independent set is likely to get lower. But what we want is a maximal size independent set. So that's why, as a greedy strategy, we try to see if I include only with fewer uncovered neighbors, that means I'm excluding only few nodes that are the neighbors of the one that we included from being part of the independent set. So we maximize the chances of the other vertices to be considered to be part of the independent set. Okay, so that's the greedy strategy. Alright, so we have 2 as the lowest number of uncovered neighbors, so we go with 2. Now there are 4 vertices with 2 uncovered neighbors. We'll break the tie in favor of the lower ID vertex, which is V1. So we'll include V1 to the independent set. So I color it as yellow. So again, as I said, once you include a vertex in the independent set, it covers its neighbors. So V4, V5 are automatically covered because of this. So they are kind of ruled out to be part of the independent set. So the only other vertices that are not yet covered are V2, V3, V6. And based on this, we should now find the number of uncovered neighbors for each vertex. So for V2, there's only one uncovered neighbor, which is V3. So that's why I say it is one uncovered neighbor. For V6, again V3 is the only uncovered neighbor, so that is 1. For V3, V2 and V6 are the 2 uncovered neighbors. So now among these 3 vertices, we should pick the one with the fewer number of uncovered neighbors, which is either V2 or V6. So we break the tie in favor of V2. So we include V2 to be part of the independent set. So when I include V2 to be part of the independent set, it covers V3. So that means V6 is by itself not covered. So it has 0 uncovered neighbors, and so that's the only uncovered vertex in the graph. So it has to cover itself by becoming part of the independent set. So V6 is now part of the independent set. So this is an independent set of size 3, and that's what is determined by this heuristic. Now again, we are not sure whether it's a maximal size independent set. We can go to the graph and just manually check if that is the maximum size. That means, is there a possibility of finding an independent set of size 4 on this 6 vertex graph? Probably not. So V1, V5, V3, that is no, V1, V5 cannot be there. So it could be V4, V3 and V5. So V3, V4, V5 could be an independent set, but that's also of size 3. So I don't think there's an independent set of size 4 in this graph. So what we determine from this heuristic is actually even the maximum size independent set. Okay, so this is the one that where non-determinism is there. So like the Dijkstra's algorithm or minimum spanning tree and all those things, when you determine the minimum spanning tree, at the end I can claim that this is the minimum spanning tree of certain weight. Similarly, when I determine the shortest path tree, I know from that source node, the starting node, what we have found is the shortest path to every other vertex. You can say for sure. And we proved that, yes, indeed, you find the shortest path tree, and we proved the Kruskal's algorithm indeed gives you the minimum spanning tree and so on. Whereas here, I cannot say for sure that what I have determined is a maximal independent set. So you have to really go through the graph and manually verify it. So that's where the non-deterministic thing is there in this in the heuristic. Okay, all right. So now once we determine the independent set, all we do is take the complement of the independent set, which is in this case V3, V4, V5, which are not in the independent set but they are in the given graph. So these 3 vertices are said to form a vertex cover. Now again, since this is a maximal independent set, the complement of that is going to be the minimal vertex cover. We cannot say for sure because this itself is kind of non-deterministic. So we have to, if you want to really make sure that's the minimal vertex cover, go back to the graph and see, is there a possibility of a vertex cover of size 2 on this graph? That means only 2 vertices, and can it satisfy the definition of vertex cover? So it means for every edge, at least one of the 2 end vertices should be in that vertex cover. So if I pick some two vertices to be part of my vertex cover, then it cannot be satisfied for all the edges, right? So based on this given graph. So if that means minimum size vertex cover at least should be of size 3 for this graph. So V3, V4, V5, we can again cross check. For every edge, V2, V3, V3 is here. V3, V6, V3 is here. V5, V6, V5 is here. V3, V4, no, V2, V4, V4 is here. So for every edge, at least one of the two end vertices is in the vertex cover. So what we determine is right. Okay, so that's how we can cross check whether you are determining the right thing. Now let us go ahead and find the maximum size clique. Okay, so for that we need to build what is called a complement graph of the given graph. So this is the given graph, so we need to now build a complement graph. So let us indicate the complement graph as G star for a given graph G. So the way we build the complement graph is we will still have all the 6 vertices. Now to decide the edges in the complement graph, all you have to do is check if there is an edge between two vertices in the given graph. If there is no edge between two vertices in the given graph, they are going to have an edge in the complement graph and vice versa. So V1, V2, they don't have an edge, so there is an edge between V1, V2. V1, V3, again they don't have an edge in the given graph, so they have an edge in the complement graph. Whereas V1, V4, they have an edge in the given graph, so they don't have an edge in the complement graph. So with regard to the layout of this complement graph, how you want to lay it out, it's up to you. So you just try to lay it out so that it's as neat as possible for visualizing. Okay, so it's up to you how you draw it out, but just make sure it is more kind of clear where are the edges in the complement graph. Okay, so once you have the complement graph, you can run again the minimum neighbors heuristic on the complement graph to determine the maximal independent set, because that's what the minimum neighbors heuristic can give you. It can only give you the maximum independent set. Again, it need not be maximum, it depends on the graph. So it can give you only the independent set, which also could be a maximum size independent set. Okay, so to do that, find the number of uncovered neighbors for every vertex in the complement graph. So count the number of neighbors. So for V1 it is 3 neighbors in the complement graph, V2 has 2 neighbors, V3 has 3 neighbors, V4 has 3, and so on. So now among these vertices, pick the vertex with a fewer number of uncovered neighbors, which is either V2 or V5. They have 2 uncovered neighbors, so break the tie in favor of the lower ID neighbor. So that's how the heuristic breaks the tie. So V2 is chosen to be part of the independent set, so it will cover V1 and V6. So V2 has V1, V6 as neighbors, so they are now covered. So that means V1, V6 cannot be part of this independent set in this complement graph. So the other 3 vertices, V3, V4, V5, now they kind of are neighbors to each other. So they have 2 uncovered neighbors. So V3 has V4 and V5 as its 2 uncovered neighbors. Similarly, V4 has V3, V5 as its 2 uncovered neighbors, and so on. So they kind of cover themselves. So the neighbors. So among these 3 vertices, pick the one with the fewer number of uncovered neighbors, which is 2 in each case. So they cover themselves along with 2 neighbors. So we break the tie in favor of the lower ID neighbor, so that is V3. So V3 is now part of the independent set, so it will cover V4 and V5. So we are done. So all the vertices in the graph are now covered. So V2, V3 is the independent set for this complement graph, because we don't have any more uncovered vertex. Now you can cross check, is that the possible size independent set in the complement graph, V2, V3. Of course there's no edge between them. Now V5, V6 is also okay, there's no edge between them. Now how about V2, V3, V5, V6? No, it cannot be, because there's an edge between V2, V6 or V3, V5. Now it looks like even a triangle is not, even 3 vertices is not possible, not triangle, 3 vertices which are not connected to each other. So it looks like V2, V3, that means independent set of size 2 is the maximum thing that we can get. Okay, so once we find the independent set in the complement graph, the claim is the same set of vertices are said to form a clique in the given graph. So again, we kind of proved it last time. Why is that? Because now the set of vertices that form an independent set in the complement graph do not have an edge between them in the complement graph, right? So for example, V2, V3 don't have an edge between them in the complement graph. That means there should be an edge between them in the given graph, because that's how the complement graph is built. To decide for an edge between any two vertices in the complement graph, we check whether the two vertices have an edge between them in the given graph. If they have an edge in the given graph, they don't have an edge in the complement graph, and vice versa. So whatever is the independent set that we determine for a complement graph, there's no edge between any two vertices in that independent set. So the same set of vertices will now form a clique in the given graph, because they are going to have an edge between them in the given graph. Like in the previous example, we determined a clique of size 3, say V1, V2, V5 as independent set in the complement graph, because there's no edge between any two vertices in that independent set. The same set V1, V2, V5 will then form a clique in the given graph, because they are going to have an edge between them in the given graph. Okay, so in this example, we just ended up with V2, V3 as an independent set in the complement graph. That means a clique in the complement graph is also V2, V3. Now again, what we find with the heuristic is it could be the maximal independent set. So the same set could also be considered as a maximal clique in the given graph. Now in the given graph, since there's not even a triangle, so these things don't form a triangle, even though it looks like it's a triangle, but they're not forming a triangle. So it looks like only an edge could be considered as a maximal size independent clique, maximal size clique. So again, any clique, any edge could be considered as a clique of size 2. Okay, so V2, V3 is a clique of size 2. So again, depending on how you are breaking the tie, you could come up with V5, V6 also as an independent set. So that is forming a clique in the independent set in the complement graph, which is a clique in the given graph. Okay, so when you work out on the graph assigned to you, it is possible that you could end up with an edge as a maximum clique, okay, of size 2. So any question on this heuristic and the three things that we found: independent set, vertex cover, and a clique? You can ask using the microphone.